In this video, we're going to talk about interest and compound interest. So if one borrows money, then one expects to pay interest. And if one lends money, then one expects to receive interest. It's usually given as a percentage, called the interest rate, of the principal over some given period. Now, in what follows, we're going to talk mostly about investing money, which is basically lending money to somebody else for them to do something with it, and then you'll receive the money back at some point in the future, plus some interest. But everything we say makes sense in terms of borrowing money as opposed to lending money. It's just the signs of the cash flows are going to change. So compound interest. So interest is computed periodically and is either paid when it's computed, when you calculate it, or it's added to the principal. If we add the interest to the principal, then for every period that passes, interest is accrued on a larger amount. So basically, you pass one period, you get some interest, we add that to the principal, and then in the next period, you earn even more interest because you're earning interest on the interest you earned in the first period. So this is known as compound interest. Now, we talk both about future value and present value. And so if we have a principal P invested at an annual rate, R, compounded M times per year, then the amount A, or future value of the account, at the end of T years is A equals P, the principal, times 1 plus R over M to the power MT. Now, a couple of things here. One, interest rates are typically quoted as 4% or 3% or whatever it is. First off, that's a decimal, 0.04, 0.03. And second, when we quote interest rates, we very rarely quote the per period interest rate. So for example, let's say we have an interest rate, a rate of 4%, compounded semi-annually every 6 months. Then the per period interest rate would be 2%. So 1 plus 4% divided by 2, giving us 2%. But we almost always quote that as a 4% effectively annualized interest rate. Now that value M, that number M, takes on some pretty common values. So compounding frequency, or common compounding frequencies are M equals 1, annual, M equals 2, semi-annual, M equals 4, quarterly, M equals 12, monthly, and daily M equals 252. So those would be the most common compounding frequencies that we see. Now, again, we had the future value equation, and we can turn it around, we can rearrange it, and turn it into a present value equation. So P is known as the present value, so P equals A, the amount we're going to receive in the future, times 1 plus R over M to the power minus MT. Equivalently, A divided by 1 plus R over M to the power MT. So P is known as our present value. One special case here is known as continuously compounded interest rates. And if interest is compounded continuously every instant of time, then our formulas become A equals P e to the RT, or P equals A e to the minus RT. Now, continuously compounded interest is very common when doing analysis, primarily because E has some really nice mathematical properties. And so we'll see this as we go forward, that there'll be times when we use e to the power RT, or equivalently, we find a rate of return by taking the natural log. We'll see that later. But we use this very commonly because the math is a little bit easier. Okay, so let's do an example. Let's have $10,000 invested in an account paying 4% of interest, compounded semi-annually. So how much will the account have in 3 years? Our formula is A equals P, the principal, times 1 plus R over M to the power MT. And we simply substitute in the $10,000, the 4%, 0.04, semi-annual, divided by 2, to the power 2 times 3, again, compounding frequency times number of years, and we get $11,261.62. Alternatively, how much should you invest today in an account paying 2% interest, compounded quarterly, so that you have $20,000 in 4 years? Again, here we're looking for present value. The present value is what we should invest now. So the present value equals A, the amount we want in the future, times 1 plus R over M to the power negative MT. So A equals $20,000 times 1 plus 2% divided by 4 to the power negative 2 times 4, which is $19,217.70. Finally, you borrow $20,000 for 3 years and must repay $21,000. What is the continuously compounded interest rate on this borrowing? So here we've got a little more work to do. So P equals A e to the minus RT. So $20,000 equals $21,000 e to the minus 3R. Of course, we could have done this differently. We could have done $21,000 equals $20,000 e to the 3R, but those equations are the same. So we have $20,000 divided by $21,000 equals e to the negative 3R. We take the natural log of both sides. This gets rid of our e because e and the natural log are inverses. So we get natural log of $20,000 divided by $21,000 equals negative 3R. We solve for R and we get 1.6263%. Final example, how long does it take for an investment to double when invested at a semi-annual interest rate of 2.5%? Turns out quite a long time. So here, A equals P times 1 plus R over M to the power MT. We want it to double, so 2P equals P times 1 plus 0.025 divided by 2 to the power 2T. We can do a little bit of simplification, cancel out our p's, take the natural log of both sides, and get natural log of 2 on the left equals the natural log of 1.0125 to the power 2t. We use the property of natural log, bring the 2t out in front, so 2t times natural log of 1.0125, and then we solve for t, and we find 58.07 years, so quite some time. Now, another thing about compounding frequency. When we first learn about compound interest, we typically learn that the more frequently the compounding, the more money we earn on an investment. Right? In 2 years, if we earned 4% semi-annually compounded or 4% compounded monthly, we'd rather earn 4% compounded monthly. That's going to be worth more. The compounded semi-annually is going to be worth less. Now, this is true. We've seen the math, we've done it before, we could actually prove, right, this is true, but this is not really the best way to look at interest. So the interest rate is a convenient way of telling you how fast an investment will grow. If someone tells you, for example, that the quarterly compounded interest rate is 3%, they are making a choice to tell you 3% quarterly compounded. They could have made a different choice. Right? Instead of saying quarterly compounded, they could have said semi-annually compounded or monthly compounded or continuously compounded. But the reality is they would have then told you a different rate so that basically your investment would grow at the same speed. So we have this idea of equivalent interest rates. So given an interest rate R with one compounding frequency, M, we can always find an equivalent interest rate R prime with a different compounding frequency, M prime, such that future values and present values with these rates are always identical. So basically, the interest rate and the compounding frequency go together. If I choose a different compounding frequency, I get a different interest rate. They'll be close, but they won't be exactly the same. So let's say both rates, we've got a rate R with a compounding frequency M, and we want to find the equivalent rate R prime with a different compounding frequency M prime. Here, neither of these are continuously compounded. So we get rid of the p's cancel. We can get rid of the t's are going to cancel. We can basically, what we can do is we can do 1 plus R over M to the power MT equals 1 plus R prime over R prime over M prime to the power M prime T. We can take the M prime Tth root, basically both sides to the power 1 over M prime T, which gives us this third row in our equation. The t's cancel, and we end up with r prime, doing a little bit of algebra, r prime equals 1 over m prime times the quantity 1 plus r over m to the m over m prime power minus 1. Okay, so we can always work from one compounding frequency to another, right? In this equation, we would know r, we would know m. Interest rate is 3% with certain compounding frequency. And we'd like to know r prime given m prime. Now, this is not a formula I would ever memorize. I would simply start with this first row, set things equivalently, and solve. Now, if we have continuously compounded rates, we can do the same thing. Here I took the tth root of both sides, got rid of the t's. Take the natural log of both sides, natural log of 1 plus r over m to the power m equals r prime. Do a little bit of simplification. We don't need to do that, but to me it's a little nicer to multiply than it is to take something to a power. And we get r prime, an equivalent continuously compounded rate, if we know the interest rate with compounding frequency m. The equivalent continuously compounded rate is m times the natural log of 1 plus r over m. So, what is the equivalent continuously compounded interest rate for an investment earning 4% semi-annually? Well, we can just take the formula we had before, or we can take the math that we did before. We find r prime equals m natural log of 1 plus r over m, or r prime equals 2 times the natural log of 1 plus 0.04 divided by 2, or 3.9605%. So, what does this mean? If I take any investment and I have it earn 4% on a semi-annual basis for some time in the future, equivalently, I could look at that investment as earning 3.9605% continuously compounded, and I will always get the same answer. What's the investment worth in the future, or what's the present value of a future cash flow? Finally, what's the equivalent monthly interest rate for an investment earning 4% continuously compounded? So this is going the other way. I want to know what the monthly rate is given a continuously compounded rate. Again, it's a substitution question. I'm trying to solve for r prime, which means I need to take the 12th root of both sides, or both sides to the power of 1 over 12. The left-hand side becomes e to the 0.04 divided by 12. The right-hand side becomes 1 plus r prime over 12. Solve for r prime, and we end up with 4.0067% with monthly compounding versus 4% with continuous compounding. And one thing you'll note is that equivalent rates, the less frequent compounding gives us a higher rate. So continuous is more frequent than monthly. So our continuous rate here is 4. The monthly rate is 4.0067. If we'd done semi-annual, it would even be a little bit higher. If we knew the monthly rate and we're trying to find the continuously compounded rate, the continuously compounded rate would be a little bit lower.